Hi everyone, so today, lesson 3, we're going to talk about the biology of the mind. So a little different from what we've covered so far, but that's okay. So we'll talk about biopsychology kind of in general, how neural communications work, the nervous system, and the endocrine system. Okay, so really every behavior, idea, mood, thought, whatever it might be, is a biological happening, right? Biological psychologists study the links between our biology and behavior. But keep in mind that while everything is essentially a biological function, some things you don't really want to study. There's just a reason to study them in terms of the biology behind them, right? So, for example, if I was looking at what leads to what's the best way to study for an exam, right? That's not something there's really any reason. There certainly is a biological basis for good versus bad ways to study, but that doesn't mean I need to know that to answer my main question, right? So the point is that a lot of stuff, yes, it is biological, but we don't necessarily have to study it that way. Anyways, so this all starts with what we call neurons, which are nerve cells, and they're really the building blocks of the nervous system. And there are 3 basic types of neurons. We'll come back to this later, but you have your sensory neurons, your motor neurons, and your interneurons. So sensory neurons, as you can probably guess, are well involved with your senses. And they basically carry messages back to your central nervous system, meaning your spine and your brain, right? So if you feel someone poking you in the back, that's your sensory neurons moving a signal from your back to your spine to your brain, right? The motor neurons do the opposite, really. They move messages from the central nervous system to your muscles so they can act. So if someone pokes you in the back again and you decide to turn around, right, the sensory neurons are taking that, someone's poking me, they're really doing that part, but then the response of you deciding to turn around and see, why is this person poking me? That's going to be your motor neurons. So they're carrying messages away from the central nervous system, your spine and your brain, to the rest of you, to your muscles, so you can act. And then you have interneurons, which kind of connect everything together. And most of your neurons are, in fact, interneurons. Okay, so let's look a little bit at kind of the anatomy of a neuron. There's a bunch of different parts, so definitely read your textbook, cover this as well, because I think this is important. You have your dendrites, your nucleus, your cell body, your myelin sheaths, and the axon terminals. So as you can see from this arrow here, the signal is going to move from left to right here. So it's going to start at the dendrites, and it's going to move along this area with the myelin sheaths, and then exit with the axon terminal. Okay? So, like we said, the dendrites, they're going to receive the message. And we'll look at communication between the dendrites or the axon terminals and dendrites of the next neuron in just a minute, or a few minutes. The nucleus is where a lot of critical functions take place, but that's not super important. Same with the cell body. The myelin sheaths is where, or kind of the area covered by the myelin sheaths is where a lot of the important stuff happens. Okay? That area right there. And then, like I said, the axon terminals is where the message gets moved on to the next neuron, which again, we'll get back to. So which part of the neuron receives messages from other neurons? This is the dendrite. So remember, moving left to right, dendrites are going to receive the message, pass it along the neuron, all the way to the axon, and then it's going to pass it to the next neuron's dendrite. Okay, so neural communication 101. So what happens is a dendrite is going to be stimulated, and this is going to send a signal down the axon to the terminals. And we call this an action potential. One important thing to note with action potentials is that they operate in an all or none law, or an all or none fashion. I'll come back to that. Action basically, what this means is this idea of a threshold is that something either happens versus it doesn't happen. There's no, it sort of happened, it weakly happened, it strongly happened, none of that. It just, once it reaches a certain threshold, everything is a go. So you could think of that as, say you were walking, I don't know, from here to, or wherever you might be, say you're walking across the street, right? That's much more of a continuous thing because you can make it halfway, you can make it a quarter of the way, stuff like that, right? Action potentials don't work this way. You either move or you don't move that way. So with that in mind, an action potential, once a threshold is met, they always occur. And now one thing you might be wondering though is, well, you obviously get sensations in differing degrees, right? So if someone is poking you in the back, they can poke you harder or they can poke you lighter, right? So if neurons tend to act in an all or none fashion, that might seem hard to believe, right? How exactly is it that we get varying degrees of strength with a sensation when an axon and a neuron acts in an all or none fashion? Well, the answer is that they still do operate always under the same intensity and the speed, but the frequency varies. So when you're getting a strong sensation versus a weak sensation, it's not that the axon, sorry, I keep saying axon, but the neurons are firing stronger or weaker, it's that they're firing more frequently. Okay? They're always at the same intensity and speed, they're just firing more frequently. So you can think of this as if you fired a gun, right? Pulling the trigger, once you pull the trigger, once you reach a certain level, the gun fires, right? Pulling it beyond that, pulling it less than that does nothing. It's just once it reaches that threshold, it fires. But also with a gun, it's not that you can fire it weaker or harder, right? You either fire or you don't fire it, but you can fire it multiple times or more frequently, right? So that's kind of the way to think of action potentials in this idea of an all or none fashion. So this is kind of a rough layout of how this process works. You'll cover this in a lot more depth when you take higher level neuroscience classes, but this is still something you have to know. So what happens is that, like we said, the dendrite is going to get stimulated. That's this part on the left here. And that's going to cause a change in this area over here. What happens is once the dendrite is stimulated, it causes a change in the electrical charge, okay? And the way it does this, and you can kind of imagine how this change in electrical charge is going to happen all along this area till it reaches the end. So it's going to shift from negative to positive, zoom, and that's how it's going to conduct a signal, okay? But you might be wondering, how does that actually occur? Well, kind of the basics of it is that if the threshold is met, like we said, what happens is these little gates open up, and the sodium ions, which if you notice here, that's what we mean by Na+. So Na+ is sodium, or ions, right? You don't need to know much beyond that. Ions can be positive or negative. So in this case, Na+ means they're positive. So sodium ions are carrying a positive charge. What happens is when the dendrite is stimulated, these gates start to open up, okay? And the sodium ions start flowing in here, right, into the neuron. Or the inner part of the neuron. And of course, since we're having this influx of positive ions, this is going to, like I said, change the charge in that area of the neuron, okay? So that's what we're showing over here. So during resting potential, nothing is happening. Then the dendrite gets stimulated, and if it's stimulated enough, beyond that threshold, gates start opening, and the sodium ions come in. This is what the action potential does. It's going to spike up. So notice how initially the inside of the neuron is going to be negatively charged. So at resting potential, when nothing is happening, it's going to start at negative 70. Once that threshold is met, the sodium ions start flowing in because the gates open. All that influx of sodium is going to shoot the charge up to positive 40. Okay? And this is kind of going to continue all along this area of the neuron. So you can imagine piece by piece, sodium ions are coming in, changing it to positive, and that's going to move this electrical signal along the neuron. Okay? So that initial depolarization influences the electrical charge. And what we mean by depolarization is that it's going from negative 70 just to a threshold that's still negative, but less negative. It is until all the sodium ions are in there that it really actually becomes positive. Okay? Also, the same thing happens. Some potassium ions also flow out, but that's not especially important. It's mainly that sodium ions come in that does a lot of the work. However, the potassium ions do go out, but what needs to happen is that as the action potential is moving along, so you can see this happening kind of all along this neuron, what happens is that the ions have to be basically reset. They need to move back to what position they're in. So as the action potential moves speedily down the axon, there's these things called these pumps, and they start moving the sodium and potassium basically back into their original position. So the sodium ions start getting pumped out, the potassium ions start getting moved back in. That's what we call this kind of refractory period. Okay? So like we said, there's a certain, or I didn't mention it yet, but your neurons can't continuously fire, right? So it's not that they just go on forever. They fire, and then they have to basically go back to normal, right? They have to return to this resting state, resting potential where the sodium ions are outside, the potassium ions are inside, right? So like you said, the way this is accomplished is that these pumps start moving things back to their locations. The sodium ions get moved out. I don't think that's really shown here, but sodium ions get moved back out, potassium ions get moved in. And that's what's going on past this peak here. So you can kind of see how things are returning to normal, and then you're back at resting potential. Okay. I'll just go over this briefly one more time. So like you said, resting potential. Once the threshold is met, because the dendrite is stimulated, sodium ions flow in. The action potential happens. Actually, I'll tell you a little bit more about the potassium while I'm on the subject. So what's kind of happening at this period is that the potassium ions start to move out, and that's how you kind of initially go back to a negative charge. Okay, so the potassium ions, so up to this point, nothing's happening, meet the threshold, the sodium ions go in. Now basically you have both sodium ions and potassium ions, both of which are positively charged. So you can imagine how that's going to shift it from a negative to a positive charge here, right? And then things kind of start returning to normal, and eventually you get back to resting potential. So like we said, sodium ions go in, you have the action potential, potassium ions flow out, this helps it return to normal, and then kind of during this refractory period, everything gets pumped back to its original position. And this takes, I don't know, like some fraction of a millisecond. Oh yeah, here it is. So a couple milliseconds for this cell to get fixed back into its kind of resting situation, and then you can do something else. Okay. And so just keep in mind that the waiting neuron, so when nothing is happening, it's polarized negatively. Stimulation leads it to depolarize because those positive sodium ions are flowing in. And then it kind of repolarizes, goes back to this negative when it's during the refractory period. Something to keep in mind is that neurons, regardless of all this positive and negative stuff, can behave in both an excitatory and an inhibitory signal. So those kind of mean really just like what they sound like. An excitatory signal is kind of spurring you to do something or spurring a response, whereas an inhibitory signal is like a brake pedal, and it's kind of numbing it down more or less. Right? So it's almost like if you had some intuit or some reason to stand up, but you also have inhibitory stuff telling you, no, I'm not going to stand up. I mean, standing up is obviously a whole bunch of muscle and a whole bunch of neurons, but that's just kind of what we mean there. It's like a gas brake and a brake pedal, right? Sorry, a gas pedal and a brake pedal, right? Okay, so review, which of the following statements is true? I don't know why I'm always teaching, but one action potential can be stronger than another action potential. Action potentials do not need to reload. They can keep firing forever. An action potential can be softer than usual if it receives a weak signal. Action potential can always occur when a response is received. Or lastly, once an action potential is started, it is self-sustaining and continues to the end of the axon. So give me a second to think about that. Well, the answer is, of course, E. Once an action potential is started, it is self-sustaining and continues to the end of the axon. So remember, if we go back here, which was the one I was looking for? This one. Once the threshold is met with the dendrites and it starts stuff going on, it starts the influx of sodium. This is going to continue all along, all the way to the axons throughout the neuron. Okay. But keep in mind that this is just one neuron, and as we'll see in a minute, it takes thousands or millions or hundreds of neurons to actually do stuff. Okay. But just kind of let's go through these other ones as well. So one action potential can be stronger than another action potential. Remember, we talked about how this is not true. Same with C. An action potential can be softer than usual if it receives a weak signal. Remember, because like we talked about, like firing a gun, pulling the trigger harder or weaker doesn't matter, as long as it's just an issue of do you meet that threshold or not. You can't fire a gun harder or softer. You can only fire it more frequently. Okay? So A and C are wrong. Remember, we talked about how action potentials do in fact need to reload, right? So after the action potential happens, you need to kind of restore things to normal. Sodium ions and the potassium ions have to get back to their initial place. Okay? And remember, an action potential does not always occur when a response is received. This is because you have to meet that threshold in order for the action potential to happen. Okay? Okay. So something that I've kind of been alluding to so far is we used to think, well, I wasn't alive then, but people used to think that your nervous system was almost like one really long electrical cord. Right? So if you get a signal, someone pokes you in the back, those neurons there go all the way to your central nervous system. And what they ended up finding out was that this can't really be true because the times don't seem to match up. There's some sort of delay going on. It's not responses are not that fast. So this kind of led to the discovery of how neurons actually communicate with another. Like we talked about, neuron, this is just one neuron, right? And once it reaches the end of the neuron, it has to pass it on to the next neuron. So it's not one continuous neuron all throughout the nervous system. And this is where synapses come in, synapses and neurotransmitters. So once a signal reaches the end, reaches the axon, this is where neurotransmitters come in. And neurotransmitters are actually chemical as opposed to electrical. So they're these little things, and they're released by what we call the presynaptic neuron. And they basically pass it along to the next neuron, okay? Which kind of receives it by the postsynaptic neuron. So you could kind of think of this as if you didn't have, say, a long enough electricity cord, right, to connect two things, what you might do is, I mean, seems strange, but just as an example, let's say you connected it to the wall, then you ran out of space, so you charged the battery, and then at the end of the cord, you disconnected it, you threw it over, and someone else disconnected it, or just connected it to whatever it is you're trying to charge. It's actually a bad example, but you kind of get the idea, right? So once it reaches the end, this gap between neurons, we're gonna overcome that with actual neurotransmitters as opposed to just electrical energy, right? So you can kind of see it here, how the neurotransmitters are passing between the presynaptic neuron and the postsynaptic neuron. And like we said, here's the axon here, passing it on to the dendrite. Okay. Now, not all of these neurotransmitters actually make it, and what can happen is that they can basically just be broken down with enzymes, which are, well, kind of like I just said from what I just said, they're basically used to break things down. So some of them can be broken down, others can be reabsorbed. This idea of a process called reuptake.